and Ehsan will introduce himself. And
Sure. Yeah, sure. So I'm wrapping up my PhD in NLP and deep learning at Carleton University in Ottawa. I also just started as a data scientist at RBC. So we'll see.
test it. Can you test it?
Yeah, of course. Yeah, okay, so should I start or?
Yeah.
Okay, so I'll just give you a quick context because I may forget in the middle, so I at least give it at the beginning. So the title is obvious: improving supervised bilingual mapping of word embeddings. It's super important. That the main reason is that a lot of times you train something, you develop this sophisticated algorithm on one language, and then you go to this other language, it's useless, right? So it's really important to be able to transfer from one domain to the other, and that's one of the good examples actually. The other thing is sometimes, so this is, in this case, the domains are languages, so from one language to the other, but a lot of times it's in between tasks, or you have, so for example, a thesis, my own thesis that's super relevant to this one is I have, for some domain, which is mathematics domain, I have some labeled data. This other domain I don't have, so I have to be able to transfer. I was super happy to see that people actually thought about it and did it. Okay, so I'm not sure if I gave a lot of. So the basic idea here is that you have word embedding. So because right now sort of the building block of almost any NLP algorithm is word embeddings, and if you have word embeddings in one language, you want to be able to, and you train your entire algorithm upon it, you want to be able to use it in some way or another in other languages, so you don't have to train on them, for example. Train your algorithm on it, but definitely you need word embeddings in different languages. Okay, let's get started. So the objective of the talk is improving alignment of continuous word representations from different languages. So you have the word cat, for example, in one language, and the task is to be able to generate the same word in the other language without supervision, without saying it before, but seeing perhaps some examples of it. Not the same word, but other words. So, for example, you've seen the word cat in, well, we'll get to the slides, but in Chinese, for example, and you try to align the distribution of word embeddings in these two languages using the words that you have embeddings and labels for in both languages. Then you want to be able to generate word embeddings. So you want to be able to generate the word, you want to be able to see the word dog, for example, in Chinese, and be able to generate the translation of it without having trained on it. So the method they leverage, by the way, the work is, the names were on the first page, people from Facebook. It builds upon generations of work, so from 2013 up to now, a few methods, including the initial word embeddings. Well, one of the most famous word embeddings methods, word2vec. So we'll see what happened. Okay, so yeah, so it uses, so the method that it employs is it uses some lexicon that it has labels for. So it knows that cat in English corresponds to this word in Chinese, for example. But there are a few, because bilingual lexicons are limited in nature, and words are just unlimited in nature. Every day, new words come in. Yeah. So the other method that it uses is that suggests this new criterion for the loss function. We'll see what that is. So this is very high level at the beginning. We get it at the end, and then you can appreciate all the differences that it makes. So proposing a new convex objective function avoids the hardness problem. We'll see what it is during the retrieval task. And retrieval here just means being able to generate the word in the target domain, given a word in the source domain. achieves state-of-the-art result in word translation task, and shows the orthogonal mapping constraint does not improve the quality of translations, which contradicts the belief so far. Okay, so I talked about the idea. Yeah, we have a small bilingual lexicon, so we have very limited a number of scene instances. The problem is a regression problem, obviously. You don't want to classify anything. You want to go from one embeddings to the other. But you want to be able to generate the embeddings in the target language as close as possible to the embeddings of the actual word in that language. Just to make myself clear, so you have a word cat, for example, that you haven't seen. You want your neural net to be able to generate an embeddings of the word cat, given the embeddings of the word cat in source language, in the target language. Okay, so it matters, because if you have such a system, then you can basically train a spam detection algorithm. Almost any NLP applications, I don't want to go that far, but perhaps a lot of the sub-applications of speech recognition, what else, sentiment analysis, even summarization, given they rely on word embeddings, you can train it on one language and then just use it on the other language. If you can just if we can just find this mapping function, which is the topic of this talk. Okay, some more background. So it's been we get to see why, but CSLS is suboptimal because it faces the hardness problem. So this talk uses CSLS. I say this only once. I try to say it only once. Cross-domain similarity local scaling, CSLS. Other methods to improve the results: semi-supervised refinement procedure, and weak supervision. So these two methods are used as add-ons to further improve. So the task is you have a distribution of words in one language. You want to be able to map it to this into the second distribution in the target language, right? You want it to map as well as possible. So a lot of methods do some initial transformation and then try to refine it iteratively. We'll see examples later. Yeah, so we'll talk about those two methods later. Yeah, so the main contribution is, I believe, and they also, a new convex objective function that they prove is convex, and therefore they can use it as an objective function and can be minimized by the projective subgradient method. So they have to use projective subgradient method because their surface is not smooth. We'll see it's piecewise linear, so you can't really, it's not differentiable. Okay, so the task, one more time, learning bilingual lexicon, given monolingual vectors. So you have embeddings for English, and then you have embedding. I gave as example Chinese, so I'm going to go ahead with it. Then you have also word embeddings for Chinese. You have these two. You want to be able to generate one from the other. Yeah. Okay. So when it says infer word translations for non-seeds, seeds are our scene data, set, which is a small lexicon. Okay. Yeah. So just some notations to get us started. So W is our the matrix, but also our mapping. They want to learn. Our entire vocabulary is 1 to n. Items, xi is the vector in the source language, y is the vector in the target language. And then our pair of seeds are xi, yi. And you see that this is 1 to small n. the reason is that the small n is the number of seeds that we have, a smaller subset of the entire vocab. And let's just assume that the vocabs are the same size in both languages. Yeah, and the last notation is going to tell us, okay, you train on the seeds, and then from n plus 1 to n, you want to be able to generate good results, or be able to map almost accurately from source to target. Yeah, so Tom McAuliffe in general likes linear mappings, and it really matters also because at first, if like the neural language model by Yoshua Bengio was really computationally, I don't want to say inefficient, but costly at least, and then he showed that no, we can just do it with a linear transformation, right? So it matters for many different reasons. So yeah, so basically you have a loss function. You want to minimize the loss function. And your loss function can be L2 norm or squared L2 norm. But we'll see that it leads to the hardness problem, and we'll see what that problem is in a bit. Oh, two propers. So it leads, it results in a linear least square problem and can be solved in closed form. L2 normalized vectors and orthogonalized constraints are believed to be believed to improve the results. So basically, it is commonly believed. Well, we'll see that the results of this paper sort of contradicts it. That if you want to do this transformation, if you want to learn this matrix W, if this matrix is orthogonal, like if you constrain it to be orthogonal, then you'll be able to save the distances between the words in the source language when you map from the source to target. So basically, if I have 2 points this distance and in the source, and I go to the target domain, they're going to be the same distance, and we're talking Euclidean distance. And then it's supposed to lead to similar cosine similarity, supposed to, because I don't think that's entirely accurate. And that's that actually is like experimentally shown to help the results for the previous version of the task, but we'll see that there are differences. It doesn't apply to the current method. Anyhow, so basically that's the definition of the orthogonal W matrix. W transpose times W is I, and D is the dimensions. Well, that's exactly what it means. So if you multiply by its transpose, it's going to be identity matrix of D. Yeah, so you obviously for this problem you can use orthogonal procrustes. Thank God I said it right. Analysis, and this is one of the methods. It's a little bit costly, but it basically does the exact same thing that I explained earlier. There are toolboxes in MATLAB that they use. So basically, you want to map one distribution to the other, and you have to find multiple transformations to do so, additions, or multiplication, whatever, but linear, obviously. And then these norms may, it's one critic that's applied to this, that using these norms, basically the orthogonal property could discard some critical information inside distributions of the source or the target, because it's an artificial constraint. Okay, so we want to minimize the loss of, so that's W, and they put it there now, Wxi and Yj for all the vocabulary. And so it's a nearest neighbor search problem in the sense that you generate, so in the previous methods, you generate this vector, so you multiply xi by w, you generate the target domain, your predicted target domain word embeddings, and then you use its nearest neighbors for the reasons that we'll see later on. But basically, you can make the decision, you can make the call if it's the right embeddings, if its closest nearest neighbor is the word that you're looking at. So for example, if you see cat in English, you generate cat in Chinese. You generate some embeddings in Chinese, and if the closest word in the embedding space in Chinese to that embedding is cat, then you did it right. Right? So you want to push for that. And the distance is L2. Okay, but the problem with this, because when you use Euclidean distance, there are a lot of words that are more frequent than others. Obviously, it's the statistical nature of embeddings, and basically they are noise to your prediction. You may more often, so they may surround a lot of words, and they may closest to a lot of words that you want to generate. So for this example, when you generate cat in Chinese, this word may be actually the nearest neighbor, but it's not cat to your embedding. So some words are close to a lot of, some areas are very dense in the word embeddings, and then you make a lot of mistakes picking the word that you don't want. And also some areas are not dense at all. That's called the anti-hubs. So so those words that are frequently in the neighborhood of a lot of words are called the hubs, and anti-hubs are the ones that just don't occur in the neighborhood of other words. So no matter how hard you try to train your system, you're not going to be able to predict them correctly. Okay, so there are two solutions of it in softmax. We're not going to talk about it much because it's not implemented. Here, well, I'm not sure, but we'll see. But there is also CSLS that we'll go in depth. So yeah. So, but the problem with these methods, so what they suggested was, okay, so now let's do cosine similarity, because that's a better, obviously for word embeddings, that's a better approach if you want to see your generated embeddings are close, at least in meaning, to the target word. But the problem is now you train you have two systems. You have a learning system, your inference system. In your learning system, you train on L2 norm. And then in your inference system, you want to use cosine. And that's not guaranteed to converge because you're using two different criteria. Yeah, so to resolve this, they suggest coherent learning and inference criteria. So basically, they with the proof that that we're going to see in a bit, they're going to show that you can use CSLS both in training and in inference. Okay, so this is CSLS. The idea is really straightforward. You can ask me about the terms if you want, but I like to think of it conceptually. Basically, you check. You want to minimize the cosine the cosine of x and y similarity of x and y. So x is your domain and y is your target embeddings, and so that's the cost function. But you want to basically push further away words that are, so let me talk about this. So you have n sub yx. Your n sub yx is the nearest neighbors of your target domain of the transformed x. So basically you transform x into the target domain, and then you look at the nearest neighbors. So that's all it means. And y prime is an element of which. So basically, what it wants to do is, so you see that it adds cost for the words that are the nearest neighbors that are closer to the generated embeddings. So what it does is actually pushes, well, conceptually speaking, pushes away the words that are too similar to the word that you're generating. We'll see some visual of it, and it'll be a little bit more simpler to grasp. But the idea is simple, and you do the same thing, like you do the reverse too. It doesn't really make sense because you're at inference it's constant, but you do the same for, so you have some now target domain, so Chinese now, you generate embeddings for your source domain, and then you want it to be close to the word and not close to the neighbors. So it pushes neighbors away. That's how I like to think of it.
What is the hardness problem again?
Oh, okay. So the hardness problem is that some words frequently occur in the neighborhood of other words. Okay. So what that means is that, say, take, I don't want to give a false example, take the word the, for example, because I know it occurs everywhere. So if it occurs everywhere, then your solution is based on the fact that you can generate some embeddings in the target domain, given the source embeddings. And then you see, you pick the closest word to that generated word in your target domain, right? And that should be so. So hopefully, if your English word is cat, then you generate some word, some embeddings in Chinese. It has the closest word to it has to be cat in Chinese, right? So it happens that these words, these hubs, occur everywhere, most likely between your Chinese cat and produced embeddings in the target domain. So it hinders your solution basically.
So essentially, the Chinese cat has too many words. If it has too many words close to it, it is difficult to pick out the right.
Exactly. So that area is dense. More likely than not, you're gonna hit one of the wrong ones.
And you want to push it out.
You want to push it away.
Push it out easier.
Yeah. You're gonna be able to.
Distribution is similar, Chinese words versus English words?
No, there is no assumption, as they don't have to be similar.
Okay.
I mean, you made the assumption that the vocabularies are the same size, I think.
Yeah, just the same size, like number of words, just for it to be easier to grasp, and it's not even that. Yeah.
So the choice of neighborhood is a choice on distance, or is a choice of number of things that are close? Independent of that, like, isn't that like extremely slow because you need to order for each point?
I don't think it's slow. I mean, we'll see. There are a couple of relaxations. Without the relaxations, it actually is. I think it also is slow, but it's linear. So I'm not sure.
But like if you choose one point,
Yeah.
you need to choose all the neighbors, and you're
I
doing
see.
that for every point.
Yeah. So you actually, so what the actual method? This is just a notation. We get to the methods, but you guess k. You look at k nearest neighbors, and then you compute on those. Yeah. Does that? Yeah.
But then if you're choosing just the k nearest neighbors, how does that actually distinguish the hardness? Because that's like the hardness is not seen just if you choose just the k nearest.
Mm-hmm.
Like the hardness is understood just by the epsilon closeness, not by the number of. Does that make sense?
I mean, you're summing over the distances of those words. So the sum of the
That's fine.
distance.
Yeah, thanks.
Okay. Well, thanks. He understood your question much better than I did. But you're actually averaging, right? So, but same results. Yeah.
That close is the close function? Do you use it?
It's going to be a closed form function. Yeah. Let's see. It's both convex and linear. Yeah.
Do you find any issues with the dimensionality? Like if your embeddings have a high dimensionality, then your distances kind of all look the same, so you can't really find them.
So these embeddings are, that's a good question. So these embeddings are pre-trained, so they're very well established embeddings. Like so I don't think you'll face any dimensionality issues. So what is there any specific issue you're?
Well, just like, for example, your distance measures tend to get like kind of wonky when you get in really high dimensions, right?
Yeah,
And
that's true.
everything kind of starts looking close.
Yeah, so like, I'm not sure what's the current dimensions. Like, back in the day, a couple of years ago, it was like 300 was very standard. Most of these pre-training embeddings are 300, and that seems to be good given the amount of core product that we have available and the net. And they're really good, like even for the ray words, they do really well. So on all these tasks, like word similarity tests, quite a bunch of tasks. So I don't think that's an issue. Okay, so basically there are a couple of assumptions. One, just to simplify the computations, is that two things. We assume that the L2 norm of the xi and yi are 1, both, and the cosine then is x transpose I wt yi, right? Because you get rid of the denominator. Okay, so and then you want to minimize this. So basically, it renders this. This is the exact same cost function as seen above. Okay, let's go to the optimization. So far minimizing non-smooth costs over the manifold or orthogonal matrices OD. And we discussed this. So one solution is manifold optimization. They don't talk about it in detail. They use packages in MATLAB. We talked about one of them a little bit. And okay, the alternative is convex relaxation. So not having this orthogonal restriction. So there are two methods that they use. One is replace your OD, a set of orthogonal matrices that you're looking at. And by the way, that's if I haven't mentioned that clearly. So that's one reason that results in your non-differentiable surface, because your matrices are just very constrained. So they replace it by its convex hull. So basically matrices with single values less than 1, which is equivalent to the unit ball of the spectral norm. We can talk about it conceptually later or at the end of the talk. And the other method, which is a looser, even more relaxes the problem, is the ball of radius square root of d, and Frobenius norm denoted by beta. That beta has to be uppercase.
So orthogonal matrices are not differentiable? It's not a differentiable
No. So most of these, none of these methods are differentiable. And that's why we use these subgradient methods. Yeah. So you have non-smooth areas. Yeah.
Can you go to a slide? One more slide. Here, back. It's funny because my PhD was in recommendation system, and it was like the relationship between users and items, and I think many of you heard about the Netflix prize. That's exactly the same algorithm that the winner, winner algorithms or winner guys.
Yeah.
It's like if you assume it's instead of the one language to another language as users, and then the other language are items.
Mm-hmm.
They exactly use the same thing. Those are the regularization for the items, and those are for users. And
Yeah.
it's funny that they.
Interesting. So they're citing. We'll see the name later. Their name was, I think it was Kano. They're citing. No, it's not Cohen. It's Kano. If I'm saying it correctly, we'll see a little bit later. I definitely cited them, and at least so they're the people who I read some parts of their paper to be able to talk about it today, but I'm not sure if they got it from somewhere else. I'm not sure, but they're so this paper says that they're the first people. Well, okay, I'm not sure about that either, but I think it's safer to say that's the CSLS method was first used by them. I'm pretty sure. Okay. And sorry about the rest over here, but you can guess. It's basically the same one. All right. There is a brief proof I'm going to gloss over. Maybe we can come back to it at the end. But basically, they prove that you can use CSLS. They prove that CSLS for their method is convex, and then you can use it as your loss function. If you want, I get back here and we talk about it in more depth at the end of the talk. So that's super important. Oh, I'm mad somewhere. Projective subgradient method. Okay, so they call projective subgradient. If somebody knows about it, tell me. But they say the method that they use is projective subgradient descent, and I don't think it's accurate to call it descent because it's not guaranteed to descend at all. Like it's a subgradient. It's not necessarily, and you actually keep the minimum in subgradient methods. You keep the minimum in case it went higher. You're going to use the same minimum that you have. So that was something that sort of annoyed me on this set. Okay. Yeah. So this is how you make your projections. I'm just going to say it. So on the set CD, your convex Hull method, taking matrix SVD and thresholding the single values to 1, and you project your beta of D, dividing the matrix by its Frobenius norm. Okay, so this is the visual that I was talking about. So at first, this is the previous method. That's a CSLS method, actually. The way if you, it helps to conceptualize. So at first, these are two different distributions. I think this is Italian. So cat in English, car, deep in Italian. And then you try to map them using the costly methods that we talked about. And then you try to look at their neighbors and pick the closest neighbor, and then you go further and refine the space so that they're better map onto each other. That's basically the algorithm that was used before, and the problem, as we noted, was that you use L2 norm squared for your learning, and then for your nearest neighbors, you use cosine, obviously. Okay, so the refinement procedure that they use, I think the third step over there, and in a few algorithms that we compare, they compare to, is basically a semi-supervised method. You have a lexicon, you learn, and then you map from source to target. Then you pick your best generated embeddings. So the word that you were, for example, closest in the target domain to the intended word in the target domain. You take that, you add it to your training set. So like any semi-supervised method. And then you iterate over. Okay, talked about those soon. Yeah, so they say that because they can use CSLS now for both inference and learning, they can use not only, because in previous method for the nearest neighbor, they only use the lexicons that they had labeled data for. But now because they're using CSLS, they can use the entire vocabulary. You don't have to have any supervised, any supervision. And that actually will help also. So details for our language pairs, this experimental details. So in 10 epochs, these numbers were set on were resulted from a validation set. Those are the learning rates, and divided by 2 when the loss doesn't decrease. And all word vectors are L2 unit normalized. And K is the number of the number of your neighbors. Okay, so experiment 1. Those are the methods. The previous method that we talked about, CSLS, that this method heavily relies upon, uses adversarial networks. I have in a slide in the end that I'll show you the details, but it's basically you have networks that you have a discriminator that tries to say, oh, this is from your target domain or from the source domain. And then you have a mapping function, mapper, that tries to fool the discriminator, that tries to generate embeddings that will that the discriminator will make a mistake on. So basic GAN approach. Okay, so the approach is, so that's the adversarial plus, so the refine we talked about, I think we know what it is. The ICP method, it's, I didn't study in detail, I don't remember much of it, but I think it's, the heuristic of the method is that if you have a trained network and you pass in a word, pass in an embedding, then if as a result of the embeddings you pass in, it generates stable outputs, then it's working well. Then it's fine. So that's the idea behind ICP. And procrustes, we talked about, it's a combination of linear functions that map the distributions and also a plus refine. So we see that, and we have the spectral and Frobenius methods that we talked about. We'll see that almost all of them, well, actually all of them, CSLS, direct CSLS outperforms the other methods. I think the average was like 3% or something.
What is the performance metric here?
Very good question. So, good question. Let me see. I'm not too sure. But I think I should take a look. But I think it should be accuracy. I guess.
Isn't it regression?
Oh, it is regression. Yeah, it is regression. So, but then what's the?
But you are picking the best mapping, right? When you do the mapping, you are picking
Yeah.
the best
So it could be. Yeah. So it could still be accuracy.
Oh, I see.
Yeah. So I think that's. I mean, I'll look at the end of the talk and let you know, because that would be deceitful not to. Yeah, okay, so two quick conclusions from this slide is that refinement minimally helps and also damages the orthogonal procedures. So this refinement doesn't always help. And preserving word vector distances seems not essential to word translation, contradicting the common belief. So this is the second experiment to, so remember we talked about previously, in the previous methods, you had to use your label words, your lexicon, to as your nearest neighbors. But here, because we have CSLS directly applied to the learning problem, you have the entire vocabulary accessible. So you can basically select your k nearest neighbors from the entire vocabulary. So that's the full. And the C's are just looking at the lexicons, looking at the embeddings from the lexicon. So you can see that there's a variety of you have a lot more unlabeled data than labeled data, therefore you have a lot more data. Okay, so by average it's like 2% more accurate. Yeah, and yeah, so they do compare it to the state of the art. It's a different word embeddings, but you see that the results are still consistent. So it's called wacky data set from Brony et al. The epochs are chosen from 1 to 10 based on validations of performance, and it achieves state of the art from English to Italian. It has to be bold, but it's comparable the reverse form, so from Italian to English. But the data, I think the embeddings were a little bit noisy. Where are the embeddings? There was some noise in the data set. State of the art, I'm not sure if I mentioned it somewhere. It wasn't an easy task for them. Okay, so conclusion. The retrieval criterion instead of score-less improves supervised learning of the bilingual mapping. Proves CSLS is convex in W, and can be used for learning, resulting in the same criterion for learning and inference. Expanded the k-nearest neighbor search to all the vocabs, not only those in labeled lexicon, which in turn improves the performance. With the novel objective function, the orthogonal mapping does not improve translation quality at all. Okay, so this is the adversarial approach that we talked about. So the first one, the first loss is the loss function for the discriminator, and the second for the mapping. Sure. I'm not sure what I want to add, but if you have questions, just ask. I think it's very intuitive. I think one thing that's noteworthy is that in LW, you look at the p theta of the discriminator. Okay, that's it.
So
Thank you.
You learn W in the process here. You optimize.
Yeah. So that's the previous method, right? So the goal is to learn W, but such that your discriminator can more accurately tell the difference between source 1 or 0, and then your mapper tries to fool the discriminator, tries to achieve otherwise.
And the
That makes sense.
discriminator is a neural network? Or?
Yeah, it is a neural network. What was the network? I don't think I did not study the architecture, but I think it was a vanilla feed-forward network. It doesn't really matter for this case because it's word embeddings, like convolutions sometimes work. Yeah.
So we have like source language and target language, and we have like a connection between some of these words, and then we are going to predict the other ones, right?
Correct.
And in those experiments, how much data, how much label data we have? Like,
Very good question. They didn't mention. No, and I want to know too. Take a look at the article again, but I don't think it was there. No, it didn't. That was my question at first, but I feel like it has to be minimal. So lexicon, bilingual lexicon. I mean, if you compare the entire, so the vocabularies, how big are vocabularies? Vocabularies can be 400,000 big, for example, right? And then bilingual lexicon, so a dictionary that has both words and like in the target and source them inaccurately. I don't think they're as big, at least. So they're sparse comparatively.
Because like it's like a coding and decoding, right? And then like when it's like you're going to decode the code, it depends like how much data you know, and then let's say with 80% of accuracy, you can predict the other words in the decoded part, you know.
So what is the key?
The key is like how much data you have, how much knowledge you have.
Yeah. So
start, you know?
yeah, good point actually. So one of the most important things about tasks built on word embeddings in general, and some deep networks that I also have used on my own experiments, is that you basically dumb down other tasks. So you look at this task, it's super complicated, use word embeddings, you can use minimally supervised systems for it. You don't even have to use a deep network as soon as you got word embeddings. So I think they're talking about weak supervision and minimal supervision. And I have parallel tasks so my task was, 30 instances, and it generalized to like 700 data points that I had, and very well, 30% improving state of the art. So I think the point of these methods is that you can use minimal supervision.
Well, what I mean is like it would be interesting if they changed those numbers and then come up with the conclusion that if we have like 10% of the labels, then we could like predict with 100% of accuracy. Because let's say we have the Asian languages,
Yeah.
and then we could like find out what the meanings of the 3 words, 4 words, 10 words, and then we could like
Yeah.
decode the Asian language.
Yeah, fair enough. I think that the smaller the vocabulary is, the less important that factor is going to be. So if we're improving your vocab size from 1,000 to 2,000, 1,000 to 1,000,000, that's going to make a difference. But from 10 to 20, or from 5 to 10, I don't know. There's going to be. So my task was like that, and I assume because they talk about weak supervision and semi-supervised learning, they had to add like one instance. They're doing an entire iteration just to add one instance, right? So I presume it's really low, the number of vocabs. Okay. If there was any questions, anywhere was confusing, tell me. I get back to it. And it was my first presentation on this talk, so.
What did you talk about?
There was a paper that came out 2 or 3 years ago from U of T on skip thought vectors, and in that paper, they discussed training and embedding on somewhat small data set, and then using a separate embedding to train on a much larger data set, similar to this, to creating a mapping between the two, to boost the vocabulary of the small data set, the embedding trained on the small data set.
Oh, I see. Very similar. I see.
Yeah, really similar. So I'm curious. This seems like it would be directly applicable to that. And I'm curious why.
So,
is it necessary to use 2 different languages in this evaluation? It might address this amount of training data issue if you use 2 different embeddings trained on different corpus in the same language, because you would have much higher overlap of vocabulary between the 2, right?
Yeah, correct.
So,
Okay, that was the last thing that you said is the topic of my thesis. Well, that was gonna be the topic at today's talk too. But I was telling a friend of mine who's sitting over there that this is this cool idea that I think is amazing to implement as the last experiment of my thesis, and voila, they did it, 2018. So that's why I talked about this, because I wanted to read this. But to answer your point, I think for them it's super important, because their problem is that for people at Facebook is that you have so many people around the world talking in so many different languages, most of them under-resourced. So like take India, for example, so many of these languages don't use a lot of writing system at all. Well, if they do, there is not a lot of labeled data on it, and basically not an entire NLP pipeline available for it. So it's super important if you can just grab the words and have word embeddings, and then you have spam detection, for example, in your or any other application that uses embeddings. You have it trained already for English, and you just map to that language, and you just use it out of the box. You don't have to train anything. Does that make sense?
Actually, did they test how these applications work with their mapping versus just training directly the word embeddings in Italian, let's say, and doing sentiment analysis? Yeah,
so the point is, here, for example, Italian is not really under-resourced. I mean, as compared to English, I think everything is, but not compared to English is not. Yeah. It's actually a good research community in NLP in Italy. So if you can actually generate closely the embeddings in the target language, you can assume that it can just do as well. If you, as compared to directly training on the word embeddings. Does that make sense? It's logically sound. So if you have word embeddings that has this distribution, I have word embeddings for English, generate a very close distribution to this guy, then it's safe to assume that it's going to perform as well.
It's going to be correlated.
Yeah, at least to high level. Yeah.
Okay, my question is going to be much more basic. So can you go back to the response function that you showed before?
So many, which one? Okay, so I think that the basic class.
You passed it.
Did I? Okay.
Yeah. Okay.
Oh, this one?
I find
okay.
this fascinating. So does it mean that, just check my understanding, there are two later
Thanks.
terms is kind of acting as a regularization for this loss function so that you dam down the crowded area.
Yeah, exactly. That's it. So yeah.
So does that mean that K, would that be a hyperparameter that you actually adjust when you are training?
That is correct. So K is a hyperparameter.
Okay.
And
does
there's
it matter for a
yes, so they tested it using a validation set, and they picked 10, I think, for most of the experiments, if not all.
10 was the largest one, or was the biggest one?
Was K. No, I think it was just 10. I think they just used 10. Yeah. Yeah, for epochs, let me check now. For epochs, they use other values. For one of the experiments, they use other values than 10 for one of the experiments. So, here. So that's for all experiments, K10. Yeah, that's epochs. So yeah, so this K was 10 entirely. And they obviously tested it on the validation set. Yeah. So the entire parameters over here are figured out.
Would be the performance, like the value increase, it kind of increases the complexity, but at the same time, people can interested to see if it is improving the accuracy as well.
I see. So you mean it increases the cost over here in the cost function, right? Is that what you mean?
This is the complexity of the algorithm because we have to recheck.
Iterate more, yeah.
More, but at the same time, we're interested to see if you reduce or increase that, you would have any impact on the actual performance.
Yeah. Yeah. So, but it's 10. It's not. We're not talking like 10 to 100, right? I think it's computationally feasible. It's linear, yeah. It's like as compared to 5, for example. You want to wait 1 day, you wait 2 days. That's what I mean, yeah.
Yeah. So. Different, right?
Fair enough, yeah. But it works well. The main impetus was to beat the other system, so we can't blame them.
Good enough to beat the others.
Yeah.
Can you show me the table that they compare different performances?
Are you asking me to show the other? Sure, absolutely, yeah. So that's the first one, yeah.
What's your opinion that I think the first row belongs to a method which is unsupervised, right?
Yeah, the first one's, yeah.
Their method is supervised.
Yeah.
So shouldn't we expect higher improvement than this one? Because it seems that the improvement is incremental.
Okay. Good point. Very good point. I like the point. So first of all, let's take it. So I really like the unsupervised methods. I really like them, but they were flawed because they were using 2 different criterions. So it's not really like, I'm not sure if I use it later on it would converge. And also the method that they're using, it's minimal supervision. So you can easily get some like bilingual lexicons. You can easily ask a person to generate 10 words for you, like from like even if in dying languages, you can go to the person and say, oh, what do you say to this device that you sit on, or this thing that you sit on in your language, and they say. So it's very easy but then it's not really vast, so you don't have tons of data to be able to make that judgment. So it's really minimal supervision. Yeah. But the fact that it improves it's because these improvements really matter. Like if you get one annoying, if you have your phone handy and then once a day it just like OK Google just comes up without you saying it, or say twice, it really matters for the user. So I think even these incremental changes do matter. But they're consistent across the board, so that's what makes it interesting. To me, just so many methods that people have tried to transfer from one domain to the other is just fascinating.
It's important that the amount of improvement they get is higher in those languages which are far more different than English.
Yeah, that's a good part of it, actually. Yeah, so because like English and Chinese, a lot of other methods are challenged, if you see. Even when you add, so where is this? English Chinese. Even when you add refinement, it lowers the performance. So they're really challenged, and it performs better. It's quite a bit better, right? Yeah, it's really good. So English Chinese is one of the hard ones. Yeah. No one wants to see the proof. Okay.
We're the only one excited about it.
I guess so.